So number 4 is where we hit the end of the road in terms of what we already knew. So we'll see why that is. So in number 4, we have we're accelerating from rest in such a way that its velocity is given by v of t equals t squared. All right, a fairly simple formula for velocity. Right, so our part A says find an expression for the hummingbird's acceleration. So a of t equals v prime of t, so that equals 2t. Part B says, is the acceleration constant? Well, the velocity depends on t, so no, it is not constant. No, v of t equals 2t is not constant, it's variable. Variable with respect to t. So part C, we're going to sketch the velocity function. So we have our 2 seconds and our 4 meters per second that we keep using. This is our velocity in meters per second. This is our time in seconds. Sketching the graph. Let's see. Yeah, v of t equals t squared. So that means that v of 2 is going to be 4. Right, since v of t is equal to t squared, v of 2 is going to be 4. So we're going to have the point 24. And since it's t squared, it's going to be a nice parabola, which has a horizontal tangent at 0, and then comes up and makes a nice parabolic shape. All right, so if we look at the area under the curve, there's the area under the curve. And it's that's our part C. It says, part D, do we know a formula to find that area? So do you know a formula to evaluate an area like that from geometry? And the answer to that is no. No, you don't. All right. Part E, do you know a formula from physics? Not unless you've taken calculus-based physics and already learned all this. No, you don't. All right. So our conclusion, F, that's what calculus is for. This is where the calculus is going to start. So all of this is about a motivation for, first of all, how this question of the distance traveled is related to funny areas, okay? So I glossed over number 3, our conjecture in number 3. It says make a conjecture about, number 3, make a conjecture about the relationship between distance traveled and the area under the velocity curve. Here it is. The area under the velocity curve is equal to the distance traveled, or x of t equals area under velocity curve. All right, so that's our conjecture. So what it shows is that there's a relationship between 2 sort of unsolvable problems. One is, I have this formula, you know, the full formula from physics, you might remember, for people who've had it, is x of t equals 1/2 at squared plus v0t plus x0, right? This only works if you have constant acceleration. If you don't know this formula, don't worry about it. I'm just saying that we have, from basic fundamental physics, an acceleration that can give us the position of an object at any time. If the acceleration is constant, the problem with which you are confronted is there are pretty simple expressions for velocity where the acceleration is not constant. Also, by the way, if you think about applied situations, so if, let's say, I am starting a vehicle. So this is all just sort of motivational about what kind of problems you can approach. You know, so we have these 2 related problems. Finding an area that I can't find. I don't know a formula for this area. All right, and finding a position function where the acceleration is not constant. Acceleration is not constant. These are our 2 related questions that we're going to draw some connections to. Well, we've already seen that essentially these 2 are going to be the same question. If I could find the area, I would know the position. If I could find the position, I would know the area under the curve. So they're related questions. All right. So I want to talk about why this non-constant acceleration is significant. This is actually what normally happens. You don't normally have constant acceleration. Object in free fall has constant acceleration. But what about when it's not in free fall? So let's say I'm launching a rocket, right? As I launch a rocket into space because I'm Elon Musk and that's what I do for a living, is I launch rockets, okay? So when the rocket is initially launched, the acceleration of the rocket is equal to the thrust of the rocket minus gravity. Actually, this is true all the time. The acceleration is equal to thrust minus gravity. But here's the problem. As the rocket moves away from the Earth, gravity is not constant. The thrust may or may not be constant. I don't know enough about rocketry to answer that, but I suspect that the thrust is also not constant. It might depend on things like the density of the atmosphere, the amount of fuel, and so forth. So the acceleration, the thrust might not be constant. Gravity is definitely not constant because my rocket's going away from the Earth, and the farther I get from the Earth, the lower the gravitational constant gets until I'm in outer space where the gravitational constant is negligible. All right. But also, if I have a car accelerating, right? So cars don't accelerate with constant. That's a car, okay? Cars don't accelerate with constant acceleration. A car goes 0 to 60 in a certain amount of seconds, but the acceleration over that time is not constant. So one thing that all types of engine have is a response curve. So they have a certain efficiency or power, a power curve, I guess is what we call it. So we have power, and that's related to RPMs, how fast the engine is turning. And different engines have different kind of response rates. So they might have a significant amount of power at 0, and that power might increase up to a point with the RPMs and then might drop off. You might have a power curve that looks like this. Steam engines have power response curves that are very high for low RPMs and then drop off significantly. So the power that the engine produces depends on how fast you're going, and the power is what gives you the acceleration. So the acceleration is going to respond to the speed that you're going at, the rate at which the motor is turning, which is proportional to the speed you're traveling. It's not going to be constant in time. Power is not constant in time. Acceleration is constant, not constant in time. So here's just a couple of examples. I want to just communicate to you that in many cases in nature, acceleration is not constant. So acceleration is seldom truly constant. The closest you can get is free fall near a planetary surface. All right, but how many things are doing that? Well, things, right, if you throw rocks at people. All right, but cars, rockets, the acceleration is not constant. Actually, for a hummingbird, the acceleration is not going to be constant. Very few things are going to have constant acceleration. So next, with all this motivation in mind, the next thing we're going to tackle is, how am I going to find that area? The question of how I'm going to find this specific area right here is going to occupy our attention for several hours. And once we're done with it, we're going to know how to find any kind of a weird area and any kind of a position where the acceleration is not constant. But we're going to start by really digging into just this one specific example and see how much we can pull out of it.